So, let's see. I'm not sure I can make a problem up on the spot. Let me see if I can find a good one. Not necessarily going to find. Maybe. Yeah, it's not easy to know ahead of time if there's going to be a bound or not. So real quick, just to go over the idea. So what I mean is if I give you something to factor, so whatever the heck it is, right? I just made that up out of nowhere. It most likely does not have the answers, because I just made it up out of nowhere. If I synthetically divide this by a positive number, right? And all the answers I get have the same sign. What does that mean? It's an upper bound, whatever the hell it is. So, what's the list of possible rational roots? Right? So let's say I try 4. Let's say I divide by 4, and I get nothing but positive results. You with me? Number 1, it means 4 didn't work because it didn't come out to be a 0 here. And number 2, that means 4 is an upper bound, which means I can throw out positive 8, positive 16, right? You guys with me? This is why every now and again I'll say, if I have a long ass list of things to try, I'll pick a number somewhere in the middle. It's got a decent chance of being an upper or a lower bound. So again, in the homework, upper lower bounds could just sort of happen as you try stuff out. That's why if it doesn't work, and what do I mean by doesn't work? Why did this one not work? What would I get here if it worked? You would get a 0 here if it worked, correct? That would mean that it factors with that piece. Is that, you guys with me? If it doesn't work, you don't just go, well, shit. You sometimes what you get, even though it didn't work, will give you more information. It told you at least that 4 doesn't work, so you can throw 4 out for damn sure. But in this case, I know that 8 and 16 don't work either, because it happens to be an upper bound. Do you guys follow? Just to remind you guys, the book didn't say shit about bounds. I told you about them, and sometimes they're stupid useful. And again, that's why I always pick a number somewhere in the middle to have a decent chance to get a bound. If I divide by a negative number, what's going to tell me it's a lower bound? So if I divide by negative 8. Yeah, if I get alternating signs on my answers, that would mean it's a lower bound. If this happened, I could throw out negative 8 because it didn't come out to be 0. And I could also throw out negative 16 because negative 8 is a lower bound, can't go below that. You guys with me? So none of the homework is going to ask you about bounds directly. But it's one more thing I wanted to give you. If it doesn't work, that sucks because you still got to try the other things out, but I'm just trying to show you. You can interpret your results sometimes to help you eliminate more from your list. I think you're at the point now where you realize getting rid of stuff in that list would be really good. Because that's all the shit I gotta try. And if I have a lot of it, I'm like, oh my God, please. Descartes, please dear God, sometimes Descartes doesn't help us. So the bound thing is just the next kind of level. So on a test, I will always have a question that says, synthetically divide by something. Interpret your results. And I'm trying to help you shorten your damn list. You guys kind of with me? I'll also have Descartes do something useful. Meaning you could throw out all the positives, you could throw out all the negatives, one of the two, right? You guys kind of with me? Okay. All right. Anything else generally or specific? Okay. All right. If there's nothing else, just to make sure everybody saw the quiz, 5.4 through 5.6. The 5.6 problem I'm going to give you. 5.6 is about rational functions, right? Asymptotes. You with me? So the problem I'm going to give you is going to be very basic. I'm not going to make it any crazy thing, okay? Y'all with me? You just have to understand, how do you determine the horizontal asymptote? How do you determine the vertical asymptotes? You with me? And of course, x-intercepts, y-intercepts, you always find those the same way, so that's nothing new. Okay. All right, cool. Okay, if there's nothing else, we're going to get right back into where we left off. Let's try it. Okay. So we got a little bit into chapter 6 last time. Section 6.1 should be relatively easy. In fact, let's do this. Let's take a look at section 6.1 homework. Let me do it this way first. There's going to be a couple things. Let me talk about a couple things first. But let's look at some of the basic homework first. Yeah, okay. So it gets a little freaky at the beginning. We'll talk about that in a minute. Oh yeah, let's talk about that because there's a lot of it like that. Oh yeah, okay. Let's do a few examples. Okay. Just got to remind myself what they start with. So can somebody give me an example of an exponential function?
3 to the x.
Yeah, 3 to the x. I love it. Kick ass. Can anyone tell me anything about the graph of this thing? What's the general shape going to be? Yeah, exactly. It could be like a logo for some weird athletic company. You know? You with me? So it's just like this. That's the shape of it. Now, if I flip it over the y-axis, it'd be like this, but it's still got the same shape. It was just flipped. So we understand now that functions can be moved around. A parabola can be moved around. It can be flipped. But it's going to still have the same U shape, right? Anybody else tell me anything else about this graph if I graph this? What's the other most important thing about this? We discovered this last time, a very interesting, weird, sort of related to what we did in 5.6, which is all about vertical and horizontal asymptotes. Does this thing have an asymptote somewhere? We discovered it last time, right? So if I raise 3 to a negative power, what does a negative power mean again? Flip. So what will this become?
3 over 2.
No. What's being raised to a negative power? What is being raised to a negative power?
3.
The 3. What else is happening to the 3?
Oh, getting multiplied.
Squared. I love it. Okay, you guys with me? So I always look at a power as being possibly multiple things it wants me to do. 3 squared is asking me to do one thing. 3 times 3. 3 to the negative 2 is asking me to do 2 things. Flip the 3, and it also wants me to square it. So it's 1 over 9. Exactly. Right? So let me see if I can push this. So what would 3 to the negative x always be? It would be 1 over 3 to the x. Is that all right? Flip it and then raise it to the x power. I can't do that because I don't know what x is. Could this ever equal 0? No. The only way a fraction can be 0 is if the top is 0, and this top is always 1. That's the whole idea of an asymptote. If I make x bigger and bigger and bigger negative, my bottom's going to get stupid big, right? I've got to fit my jeans in. But it's never going to get to 0. So 3 to the negative million is going to be 1 over 3 to the million. It's going to be a stupid small number, but it's still going to be greater than 0. Yes? for most humans, 1/3 to the millionth power is like 0, but it's not quite 0. So then I know this sucker is going to have an asymptote here. What is it at 0? What do I get when I put a 0 in this?
1.
1. And of course, as they get bigger and bigger, 3 squared, 3 cubed is just going to go up like crazy. Okay, so that's what we did last time. We investigated the shape of this. We discovered there was an asymptote. I didn't have to know ahead of time there's an asymptote. I just found out, oh shit, there's an asymptote. Okay. So, let me fill in a couple more specific points on my beautiful graph here. What do I get when I plug a 1 in? My scale sucks. Let's do this a little better, Jeff. So if I have 3 to the x, let's make a little bit better graph. So when I put a 0 in, I get 1. When I put a negative 1 in, what do I get?
-3?
No.
1/3.
What's f of negative 1? 3 to the negative 1? 1/3. And when I plug a 1 in, of course, I get 3. 3 to the first power is 3. Is that cool? You could do it, Jeff. There you go, buddy. So this would be like a base function, and then I could do something like this. How would I do this? What are the shifts? Yeah, right 2, up 1. So we'll take this point, right 2, up 1. It would take this point, right 2, up 1. It would take this point, right 2, up 1. Where would the asymptote go? Remind me, how long is the asymptote? How long does it go?
Forever.
Forever. So if I move it left and right, does anything actually change? No. So the only thing in here that's going to move the asymptote is when I move it up 1. So where does the asymptote end up? It's at 0 now. If I move it up 1, where is it? 1. Is that y equal 1? And that's exactly matching up with what's going on here. So again, the old ideas that we've applied before about shifting functions, they're still going to work. The whole thing about transformations of functions, they don't care what the function is, they just move it the same way all the time. All right, maybe. Would you say that this models growth or decay? What's happening as I let time pass? Is it growing or is it decaying? Yeah, as I let time pass, it's growing, correct? In fact, this is exactly the kind of function I would use to model population growth. You guys with me? We're going to learn a number here later. It's a lot like pi. Well, it's a different number. And it's actually the number that helps us model growth better. But an exponential function models growth. How would I make it model decay? I want it to go down over time. How would I have to change this picture so it would go like this? I'd have to flip it over the y-axis, correct? So be careful. So I think you said it right there, Mike. If I do this, how does that change it? Say again?
It decays.
Well, sure, but it would do what to the picture?
Well, it would flip it over the.
Yeah. So again, just reminding us, anything with the x is a left-right shift, change. So the negative means reflect. Since it's with the x, left-right. So now it's going to look like, just a rough sketch, it's going to look like. So over time, if I let time pass, this is decaying. Now, decay is a weird word. Decreasing, but we normally say decay because one thing this is used for is like radioactive decay. If you have a piece of radioactive material, over time it's going to emit that radiation. It's going to become less and less radioactive. So that's like, for example, Chernobyl. You all know what happened in Chernobyl. I know it was before you were born, but you still know about it. Do you want to go to Chernobyl?
Yes.
Oh, you might want to. I don't know if you ever saw that. I never saw the horror movie. I don't know if it's any good. There are people still living there. They're probably not doing well because it's going to take thousands of years for the radiation to decay to a level where it's safe for humans. You guys semi with me? Okay. So that's why we call it decay when it's kind of going down, because it's related to radioactive decay. Okay. So if I said, does this model growth or decay? Growth. Does the -2 actually change that? No. The x is positive, correct? It's just going to be shifted right too. It's still going to go up. You guys with me? Okay. Let me throw a curveball at you. Is that growth or decay? What do you guys think?
Well, if it was like 1/4 of the x, I would say decay. But if
That is what it is. Yeah.
Huh?
That is what it is.
That is what it is?
That is what it is.
Well, I mean, 1/.
That is what it is. Right, so what is 1 to any power? 1. And then 4 to the x. So is that what you're saying?
Yeah.
Mike? That is what it is. But here's a better way.
Oh,
And Mike, you're like, stop saying that is what.
okay, so.
1/4 is 4 to the what power? You could do this. We just talked about this.
Minus.
Yeah. 4 to the -1. Is that cool? That's what 1/4 is. You with me? What do I do with powers like this? When I have something with a power raised to a power, what do I do with these?
Turn it to a fraction?
No. What? Alright, let's a little review. Okay. Help me out. What's x squared cubed? Wouldn't that be x squared times x squared times x squared? Because that's what frickin' cube means, right? How many x's do I end up with?
6.
So what's the shortcut? Never do that shit. What's the shortcut?
You multiply.
Multiply, okay. You guys kind of with me? Again, so students get this mixed up all the time. What's this? X to the 5th. 2 x's, 3 more, of course there's 5. This says 3 groups of 2. Isn't that the most basic definition of multiplication? 3 groups of 2 x's is x to the 6th. Let me stop for a minute. So coming back to this would be what now? And is that growth or decay? Obviously decay, I love it. So if there's a fractional base, and they're asking you if it's growth or decay, because if they give you a problem like this, can you tell if that's growth or decay? Well, how do we write 1/5? It's 5 to the -1. And then what do you get? Positive x, so is that growth or decay? Growth, I love it. So as time goes by, if x is time, and I let time go by, this is just going to grow. Is everybody with me? A little bit, okay. But let's talk about for a minute what this physically means. Do you remember the problem I gave the other day about I'll give you a cent on one day, and then the next day I'll give you double that, and the next day I'll give you double that? Okay. Or I'll give you $1 million, right? And let's say this is a month with 31 days, just to make this interesting. So the first day I give you 1 penny, and then the next day I give you double that. You guys are kind of with me. So watch this. Day 1, I give 1 cent. Day 2, I give 1 times 2. Day 3, I give 1 times 2 times 2. Right? I just keep doubling it. You guys with me? So day 1, I'll give you 1. Day 2, I'll give you 2. Day 3, I'll give you 2 squared. Are you guys all with me? So what about day X? See if you guys can see this.
2x.
Careful.
2x.
This was 3rd, this was 2nd, this was 1st. What about day X? Right, on the 2nd day, 2 to the 1st. On the 3rd day,
2 to the x minus 1.
yeah. Let me stop for a minute. You guys all see that? It's just because the first day I hadn't doubled anything yet. So don't I double one less day? Because I start doubling on the second day. You guys kind of with me? That's a little tiny detail. It's okay. What would you have to do to figure out how many pennies am I going to give you on the 31st day? Two to that. Yeah, so 30. Try to do 2 to the 30th if you have your calculator.
Gives you an E.
1073741.
Wait. Do it again.
1073741,824.
Okay. This is cents, correct?
Mm-hmm.
So I make it dollars by doing this. Is that cool?
Yeah.
See, now it's dollars. Everybody with me?
Mm-hmm.
So how many dollars is this?
10 million.
It's $1 million. So if I said I'll give you $1 million right now, or I'll give you a penny today and then double that tomorrow for the next 31 days. Right? Now, a lot of people have heard this by now because I've seen this like on YouTubes or whatever. But some people haven't, so they'll probably say, I'll take the $1 million. I'm not going to take pennies. But not only would you get this on the 31st day, let me see if you guys get this. How much money would I give you on the 30th day? What's a quick way to get that?
Divide by 2.
Yes, if I divide this stupid thing by 2, I'll figure out what I get on the 30th day. So I'm not just making $10.7 million because on every day I'm giving you money. Do you guys see what I'm saying? So the previous day I would have given you $5.4 million roughly. You guys kind of with me? Okay. What other thing? So this is a little bit contrived. What else grows exponentially, do you think? Do you guys know anything that grows exponentially? Anybody taking any biology or chemistry? I know several of you guys are taking chemistry, huh? Bacteria. I love it. You leave some bacteria in a little dish, and you come back later. Right? Gross? Yeah, gross. Okay. So we get the idea so far. Yeah. Sit down very creepily, but you might. All right. So this specific example is not terribly important. What's important is the idea it gives us. So what would change in all my work if I tripled it every day instead of doubling? What would change in this formula right here if I was tripling it every day instead of doubling it? That would be a 3, yeah. So when I see a function, when you see a function like this, I'm sorry, were you done? Whoever asked me to move it? I guess, okay. What does that represent? If I think of it as each day, how much am I multiplying by each day? 4. And it makes sense. What's on the 0th day? What do I start with?
0.
No, what's 4 to the 0?
Oh.
Well, I keep doing this, I'm sorry. You guys with me? So then I take that 1 and I multiply by 4, that's 4 to the 1st. And then I multiply by 4, that's 4 squared. Okay, cool. So basically exponential functions capture repeated multiplication. So we see, have you guys ever heard, not the video game, but the idea of half-life? The half-life of something? You ever heard of carbon dating? That we can measure how much radioactivity is left inside of a thing and tell how old it is roughly? Okay. So half-life means something is cutting in half every now and again. So for example, the kind of radioactivity in Chernobyl, the half-life I think is like 5,700 years, if I remember correctly. So it takes 5,730 something years, I think it is, I could be very wrong, for the amount of radioactivity just to cut in half. You guys kind of with me. So that's what half-life means, is how long until, kind of makes sense, how long until there's half of the shit left, right? And then of course we got this, here's the safe level, how long until we're to the safe level? A long time. Okay. Okay. A couple other things. one thing they give us in this book, and I'm not gonna spend time, kind of going over this too much. But let me just write this down. Let me make sure that I use the same, I think the book, because I am not interested in business. I think they show both. Let's make sure they show both equations. There's that one. Here. There. That's that one. Do they show both? No. Alright. That's fine. I don't want to show more than they do. Okay. Oh, sorry. What's up?
Was the one of the unit?
Not yet. That's weird. We're getting to E in a minute. So let me do the same thing they do. It's coming back to one. Alright, this. Has anyone ever seen this equation before? Does this look at all familiar to anybody? Some of you guys? Do you remember what it's for? Yeah. So P is the principal, it's how much money you put in. Let's see if this makes sense. Do any of you guys have savings accounts? Okay. Remember my college days would be like, savings account, right? Sorry. So it's nice you guys have savings accounts, that's all. You put a certain amount of money into the bank. I always forget if this is I think it's principal, or is it principal? Al, okay. That's the amount of money you put in. R is the interest rate. T, thankfully, is the amount of time you leave it in. Normally it's in years. N is the weird dude. So let me ask you this. Let's do one concrete example of what's happening here. Okay. Just so I can explain what N is. Let's say I really don't want to spend a ton of time on this. Let's say I put $1,000 into a 5% account. And let me just use normal English for a minute. They add interest every year. So here's the not so normal English. We call this compounding. So they compound it once a year. You need to do this. Let me stop for a minute. So all the word compound means is how often do they put interest in. Now real quick. If they put the interest in more often, I'm going to make more money. Because once they add the interest in, then the next interest is going to be based on that bigger amount. Are you guys understanding? So if they do it once a year, my money grows every year, and then they put the interest in at the end of that year, and then the next year it's growing on top of that. If they do it every month, then how many times do they compound it a year? 12. It's crazy. Holy shit. Which means at the end of a month, they put more money in, and then the next month it would grow on top of that. Are you guys? So if I put the same amount of money into a 5% account that does it once a year, I'm going to make less money than if the account added it in every month. Does that make sense? Because now my money's making more money. The old adage, you need to have money to make money. So true, right? Okay. So let's do this specific example. Can anyone tell me, I'm doing it once a year, so at the end of 1 year, how much money am I going to have? What's the amount of money I'm going to have? How would I figure that out?
1,000 plus 5% of 1,000.
Good, 1,000 plus 5% of 1,000. Let me write this in kind of a strange way. 1,000 times 1 plus 0.05. Is that okay? I can write that weird way. I can just kind of factor a 1,000 out. Just to point this out, do you see how that's related to this amount times 1 plus r? If n is 1, I'm not overly concerned with this formula, but I just want to show you some concrete example. So then how much money am I going to end up with? What's 5% of 1,000? What's 5% of 100? It's 5% of 100. 5, because percent means out of 100. So what's 5% of 1,000?
50?
50. Ooh, look at me. I won. I earned $50. Watch it. Yeah. So at the beginning of the next year, assuming I didn't do anything with my account, it's got 1,050 in it, right? So how much money at the end of this? So this is the first year. How about the end of the second year? The amount's going to be based on how much now? 1,050 plus 0.05 times 1,050. Or 1,050 times 1 plus 0.05. I almost don't care about the answer, but you can get the answer. What's the answer going to be? Was that 5250? So it'll be 1102.50. Is that right? Okay. I almost don't care about the answer. So real quick, I just want to make this clear. The 1,050, wasn't that 1,000 times 1 plus 0.05? Yes. Okay. And then I took that amount and I multiplied it by 1 plus 0.05 again. Just want to make the equation make a little more sense. Wouldn't this be 1,000 times 1 plus 0.05 squared? Okay, so now looking back at the equation, if I make this equation, real quick, if I make n1, it becomes this. Do you see how that's exactly the idea? The interest rate is 5%, the amount I put in is 1,000, and I'll let it stay in there for 2 years. So if I did 3 years, I could just put a 3 here instead of having to go step by step by step. I could predict how much money I'm going to have at the end of whatever number of years. You guys kind of with me? Things get weirder. So why is this equation worse? Because if I do it every month, I would apply the rate divided by 12 each month. And so let me ask you this. If I left it in for 2 years and I compounded it every month, so how many times am I compounding per year? 12 for 2 years. So how many total times am I compounding it? 24. So n times t, 12 times a year, times 2 years. NT just means the number of times you're going to do this thing. That's all it means. That's all I want to spend time on this damn thing. I do not want to spend time. I'm sorry. I spent way too much time on this. I almost don't care. So for your homework, it's going to be a bunch of plug and shove shit. But this is a good representation of an actual place in real life where exponentials are used. It happens to be a very boring. Now, if you love business, I'm sorry. Of course, I love math, so look at me. I can't talk. It's like, you love math, man. What the hell are you talking about? I am not a business person, though. I hate it. Okay. All right, so you're going to see this in the homework. Does everybody kind of understand better what these variables mean? The amount of money you put in, the number of times per year. So if I do it quarterly, if I compound it quarterly, how many times a year is that? Yeah, because how many quarters in a year? 4. It's crazy. Semi-annually means twice a year. Okay, you guys kind of with me? So the word problem they're going to give you, you can first figure out what n is, based on, do they say annually, do they say quarterly, do they say monthly? They'll tell you what the rate is, and they'll tell you how much time goes by. So then it's just a bunch of plug and shove. So it's kind of making sure you know how to use this formula, and then it's making sure you know how to plug it in your calculator. Okay. Enough of that. Next thing. Looking at, well, I said enough of that, and I'm going to bring it back a little bit. There's something kind of nifty about this. So real quick, if I take, and again, this is just for a second, I'm going to do this. If I let R be 1, and I let N be N, and I let T be 1, and I'll let P be 1. So if I put $1 into an account earning 100% for 1 year, that's this idea. If I let N be 1, that means I would compound it once. So real quick, if I'm earning 100% interest after one, and I put $1 into the account, how much money should I have at the end of the year? $2. I love it, right? And sure enough, if you plug a 1 in for n, you'll get 1 plus 1 is 2 to the first powers. If I compound it more than once, I should end up with more than $2, correct? So let's see. If I do it once a year, I'll get 1 plus 1 over 1 to the first power. That would be 2. Amazing. If I do it semi-annually, so twice a year, this would be 1 plus 1/2 to the second power. Can somebody help me with that? What is 1.5 squared?
2.25.
2.25. So I'd earn a little bit more money, correct? You guys with me so far? So this is exactly what I was saying earlier. If I compound it more often, I'm going to make more money because I'm going to have more money to have the interest of. What about if I do it 10 times a year? Let's make it 12 to make it monthly. Can somebody do this for me? So in your calculator, put parentheses 1 plus 1/12, close parentheses to the 12th power. Let's see what we get. How you would put it in 1 plus 1/12 to the 12th. Did anybody get that? Anybody trying?
Yeah.
2.613.
Yep, 2.613. Blah 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 blah. Let's do it how about if I do it just almost every day? So I do 1 plus 1 divided by 360 to the 360. Why is making? Oh yeah, that's right. Because I had. Wait, let me change this. There we go. No, that's the old one, Jeff. 1 plus 1 over 360 to the 360. So I get this. Just to cut to the chase, let me do 1 plus 1 over 10,000 to the 10,000. If I do, you guys all with me still? So this is if I do it 10,000 times a year. If I compound it, I add the interest 10,000 times. So what if I do it 100,000 times a year? It seems to be settling on a specific number. Do you guys, real quick side note, do y'all know where pi came from? Don't say the other. Do you know where pi came from? You guys know where pi came from? So if you take any circle, I don't care how big or small, and you take its circumference divided by its diameter, you always get the same number. So the Egyptians thought it was about 22 divided by 7. That's pretty close, right? It freaked people out. I don't care how big or how small you make that circle, if you take the circumference and divide it by the diameter, you always get the same number. Are you guys semi with me? Freaked people out, so we gave it a letter. We're like, ooh, that's a special number, let's call it pi. That's basically the history of that. This number is kind of equally weird. Why the shit should this be this specific number? So we give that number the symbol E. Just like we gave pi 3.1415, that's blah, 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 blah. Now, to be really honest with you, this is not the most interesting place E comes from. If I take the function 1 over x, do you guys see if I draw lines, I can get like an area right there? You guys kind of with me? So if I start at 1, how far up do I have to go until this area is exactly 1? I have to go up to E. Now, I understand if you don't agree with me that's interesting. But I think it's a little more interesting than this, but that number just magically makes that happen. So there's a few places E comes from, so we decided to give it a letter. So E is approximately this number we just got. And in fact, you guys see your E button? Mm-hmm. Yeah, it's above these freaky ass little ln and log that we're going to talk about very soon. So if I do second ln, and I put it to the first power, it'll tell me what E is. Why is it not exactly that last thing I had on this? Because here's what E really is. If I kept going with this, and I let n go to infinity, no, stay with me. What does this go to as n gets really big?
Gets smaller.
It gets really small, right? So basically the inside becomes 1. Does it ever actually become exactly 1? But this approaches 0, so this inside approaches 1. The power is just going crazy, yes? Getting bigger and bigger and bigger. Are you guys all with me? So 1 to infinity would be 1. 1 to any power is 1. Are you guys kind of with me? But this is never 1. So it kind of like has these competing things. It would be 1, but it's not 1 because this is never quite 1. So it just comes out to be this number, 2.71828, blah, 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 blah. Let me stop for a minute. All right, Jeff, I think you've made it appropriately clear that it deserves a little letter because it's a very interesting number that comes out of a few different places. Okay. Now what's really nifty is if I use that number as a base, now obviously this would be gross to draw by hand because E is 2.718, blah, 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 blah. It's like, holy shit, I can't draw this by hand, so we're not going to worry too much about that. It still has the same shape. I mean, here's the basic shape. This is 1. It still has the same shape. But what this does really well is it models growth. So for example, if I had something that was growing at 1% each year, I can model that with this equation. Continuously growing at 1%, I should say that. Continuously. Okay, let me stop for a minute. If I only put interest into my account at the end of a year, it's not continuously growing, is it? It grows in one big chunk at the end of the year. If I do it every 12 months, that's closer to continuous. If I do it every second, that is way closer to continuous. If I do it every instant of time, that is truly continuous. And that's what E does. E represents truly continuous growth. Or decay if I make it a negative power. Maybe. So in general, if I have this, K is the percentage growth. So let me show you, let me see how let me show you this in the book here real quick. Okay. Here's where they kind of step through the stuff we just did. So you get that E number. Blah, 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 blah. Here we go. Continuous growth. Blah, 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 blah. Yeah, R is the continuous growth rate per unit time. I used a K because I'm just using a K. Sorry. Let's see. So here, compounded, so continuously growing, you must use the E, dude. And it's growing at 10%. Oh, they do, that's right, they do that. That's what I wanted to check. So let's see, coming back to this. If it was 1%, this would be, come back to me, there it is. This would be 0.01. Yeah. That makes more sense. So K is the percentage growth. Why did I put a 1.01? I was thinking, yeah, okay. What would it mean for it to be decay? The same thing as always. What would have to be true about, let me call this R like they do. What would have to be true about R for this to be decay? R would have to be negative. I love it. So here's an example problem you'll see. I start with 100 bacteria in a Petri dish. Growth rate is 3% per hour. How many bacteria in the dish after 7 hours? Question. So I've got my function. I'll call it A for amount. And then I have an initial amount, e to the rx. I think the book, yeah, this makes more sense. I always use x for everything, but I think the book makes it a little bit more direct. They use t for time, makes more sense. And then you got pert, I love it. So what do I tell you in the problem that you can just plug in?
The 3%.
Good, 3%, we go in for what letter?
The R.
The r. And what do I actually make r equal to? Not 3, right? But
0.0.
0.03, I love it. What else do I know? Where does 100 go? P, that's the initial amount, right? And then, what else do I know? Time is 7 hours. A little thing, I don't think the book does this, but you gotta make sure these are the same units. Does that make sense? If it's per hour, I gotta make sure this is hours. So if they would have said a day, I would have had to make it 24, because it's 24 hours. So you gotta make sure these units are the same. And then, let's see if you guys, can you just, if you have your calculator, I didn't bring mine with me, sorry. If you have your calculator, can you try to plug this in? Don't say anything. Try to plug that in. Be a little careful up here. You gotta make sure that all of that's in the e exponent. If you have a newer calculator, it's easier because you just don't come out of the exponent until you get the times 7 in there, right? I'll do it both ways in mine. If you don't have a calculator, just sit there and
And
hang
what
out.
does the R stand for? The
R
rate?
is the rate of growth in this case, or the rate of decay, just the rate of change. So using R makes sense. Sorry, let's look at 71. So this is how I would put it in, because I got one of the newer calculators. Ooh, look at me. Is that what you guys are getting? I like it. Let me see if I can make it look the other way. I think I can. There,
Can you
this is
go
what it
up
would
just
look
a little
like
bit?
if you have one of the older calculators.
Can you move the paper up just a little bit?
Sure.
Thank you.
And of course you get the same answer. You guys with me? The thing you want to be careful about is don't do this 100 times e to the 0.03. Well, this is nice because it opens a parenthesis for you. But you don't want to do this because what that does is it does this, and then it multiplies all of that by 7. Very different answers, right? That 7's got to be in the exponent. You don't want to come out of the parentheses. Okay. So what if I let a full day go by? So now I got 200. So the doubling time for this bacteria is a little less than a day. Does that make sense? In one day, it a little more than doubled, correct? So I'd say a good estimate for the doubling time would be just a little less than a day. So how much should there be after 2 days?
410?
400 something, yeah. Doubling time is roughly a day. So if I do 100 e to the 103 times 48, sure enough, it's a little more than 400. 3 days, it would double again. So we got half-life. We can also talk about doubling time. Okay. All right. Okay. So you're going to have some like wordy problems where you just have to identify what the variables are and plug them in. How do you know when to use E? When they're talking about continuous growth. Use the E dude. Okay. All right. Now we're getting something nifty. And I can't remember if I asked you guys, I'm pretty sure I did. Asked you. This is just graphing, we already graphed stuff. 6.3, we get into logarithms. So let me explain what a logarithm is. Is that the right time? No. What time is it? It is the right time. Incredible. Okay. I think this is right. Is that right?
Yeah.
Okay, good, thank you. I'm just surprised that the college actually updated the class. Does anyone know anything about logarithms besides you hate them? Yes, what do you know? Yes. Okay. Understood. I'm with you. So, let me ask you guys a silly question. What is the square root of 64? You've internalized what that symbol means. That symbol is asking you to think backwards. Do you guys agree with me? You didn't actually do something to 64. You thought backwards. What do I take 2 of to multiply to be 64?
8.
Beautiful. I love it. So help me out. 2 to what power is 8? 2 to the third power is 8, right? Same way I could say 8, I'm sorry, what squared is 64? The exact same way. Are you with me? True, and see, that's the question this thing is asking. So let me focus on that for a second. What is the cube root of 64 asking you?
What time to the third power is equal to 64?
Exactly, right? This is not good enough. We want to have a symbol, and the symbol we chose was that one. Like it or not, that's the symbol we chose. You guys have internalized the question that that symbol is asking you. So you do it without even realizing you're translating. Sort of like you guys know a little bit of the foreign language that is math, so you don't have to translate each time. You just kind of know what that symbol means, right? Same thing's going to happen with this logarithm dude. So this is not good enough. I don't want to have to write little question marks every time. I want to have a function that means this. The same way I have a function that means this. This function is asking what base do I raise to this power to make it 64. This function is asking what power does the base of 2 need to become 8. So they are related, but they're definitely not the same thing. Do you guys agree? Mm-hmm. So I can't just use a root notation for this because I know the base. So unfortunately for everybody, the symbol they chose is based on an old Greek word, a couple of Greek words. Logarithmos, which is the study of numbers, study of ratios actually, but so they chose to use this. So the way they rewrote this, in much the same way that we decided to rewrite this, we rewrote this into this form to make it more compact. So I have a function kind of operating on something. Makes it so much easier to solve equations and so forth, so I don't have to have a bunch of little question marks running all over the place. I don't want to do this shit forever. So what we do is, what's the base in this question? 2. So I'm going to put it down here. Log base 2 of 8. This symbol is just asking you, what power does this need to become this? And of course, what power does 2 need to become 8? 3. You guys all with me? So again, bad choice of symbol. A little freaking word. You get all kinds of stupid ass jokes. There's one about a log cabin. I don't care, right? So we chose a little word to be a symbol for a function. That is weird. But the square root symbol is actually at least as weird, to be honest. But at least it's not a little word. I think that's part of what turns people off to logarithms is it's the first function we ever saw that was a word. It's like, ugh. But now the reason another reason people don't like it is because you haven't internalized the question yet. So you gotta have to translate each time. So what question is this asking you?
How many times do you have to square 3 to make
No. Careful, I think you mean the right thing, but you said square.
Oh, not square. Oh, cube. Or how many times do you have to raise the power to 3 to the power 2 to make 27?
Alright. What power does 3 need to become 27?
3.
Is that cool? Another way to say it is, how many 3's do you need to multiply to make 27? So yeah, 3, right? You guys follow what I'm saying? So of course you can't do logs if you don't know what the question that symbol means, right? But that's all the question that symbol means. What does this base need as a power to become this? So notice, the answer to a logarithm is always a power. So when we talk about the properties of logarithms, they're going to be exactly the same as the properties of powers. Because that's what logs are. So yeah, this is the third, this is 3, why? Because 3 to the third power is 27. The same way I could say cube root of 64 is 4 because 4 cubed is 64, right? Let's stop for a minute. So don't say anything. Think about this one. All right, who's got that?
4?
Yeah. Why is it 4?
Because 2 to the 4th is 16.
Yeah. Or another way to think about it, it takes 4 2's to multiply to be 16. How you guys doing so far? If you've done logs before, is this making sense? You might have been like, yeah, this made sense, I just don't like it. Okay, well. So when could they get a little weirder? When can they get weirder? Remind me, what power is a square root?
2.
No. 1/2. I love it. Because what's the square root do to a number multiplicatively? It cuts it in half. So another way to write the square root of 64 is 64 to the 1/2 power. How do I write the cube root of 64?
64 to the 1/3.
Holy shit. Okay. So what does it have to do with anything, Jeff? I'll show you. What is log base 8 of 2? Now let's think about this for a minute. It can't be bigger than 1, because 8 to the first power is 8. So it's got to be something that cuts 8 down.
1/3.
Yeah. 1/3 of 8. If I cut 8 into 3 parts, what is each part?
2, 2, 2.
2, 2, 2. Right? Let's see if you guys are with me or not. So let me show you something kind of cool. And you're like, it's about time. What was log base 2 of 8?
3.
3. Log base 8 of 2? 1/3. Why does it make nothing but sense? 3 2's make 8. Therefore, 1/3 of 8 multiplied by 8 is 2. It's they kind of just the reverse of each other. Do you guys see that? What about this? This one's not as difficult. Again, what are you thinking? The answer to a logarithm is always a what? It's always a power. What power does the base need to become the inside number? What power does 8 need to become 1? 0. Anything to the 0 power is 1. Are you guys good? Okay, I love it. So log base anything of 1 is frickin' 0, right? What about log base 8 of 1/8? Let me make sure this makes sense. Log base 8 of 2 is a fraction.
-1.
Yeah. Log base 8 of 2 is a fraction. Log base 8 of 1 is 0. So log base 8 of 1/8 has got to be less than 0. Yes? because now the inside's smaller. And sure enough, how do I get 1/8 from 8? I flip it. And what power flips things? Negative powers. So again, the thing to internalize about logarithms is when you see a logarithm, this is what it's asking you. What power does the base need to become the number inside? What power does 8 need to become 1/8? It needs a -1 power, so it flips. That's all they are. That's it. So let me give you a little freakier problem, of course, and give you another way to kind of like work it. What about log base 8 of 16? I'm going to give you 2 ways to work this. I'll do the textbook way, and then I'll do my way. Do it my way.
4/3.
We'll get there. Yeah, you're right. You probably did it my way. I like it.
I just did it.
Yeah, I'm with you. So for the rest of us, do we know the answer? No. So I'm going to call the answer, incredibly enough, what do I do in algebra when I don't know something? I call it x. Are you guys at the point now, what does this really say then? 8 to the x equals 16. Is that cool? Let me stop for a minute. I can always rewrite a logarithm as an exponential because they're related to each other. So how does this help me, Jeff? Well, let me show you. What number are both of these based on exponentially? What's the base for both of them? 2. 8 is 2 to the 3rd. 16 is 2 to the 4th. If you can write each of them in terms of the same base, you can do what I'm about to do. What happens here?
3x.
What is the only way 2 to this power could equal 2 to this power?
Add 1.
Those 2 powers have to be the same. Those 2 powers, what's the only way 2 to something could equal 2 to something else if those are actually the same thing? 2 to the 5th cannot equal anything else except 2 to the 5th. You guys with me? So this statement says 2 to this thing equals 2 to that thing, so those have to be the same. Yes, sir? You good? Okay. So I get 3x must equal 4. Does everybody really see what just happened there? In order for this to be true, this must be true, and sure enough, we catch up with Philip up there, we get 4/3. You can always do that. You shouldn't have to do that a lot, but you can always do what I just did. Well, I gotta be careful. As long as these are based on the same number, right? Later we're gonna talk about what if we can't do that shit, then I'm gonna need the calculator's help. Now, the other way, real quick, I just wanna show you the way that I think Philip and I both probably do it. What do I have to do to 8 to make it become 2? What power does it need? 1/3. So if I cut 8 into 3 parts, I'll get 2. And then how many of those do I need to make 16? 4. So I need 4 of these to make 16. So what power do I need? 4/3 power. Same answer, different way. If this way doesn't make sense, don't do it this way. Sort of like if you forget to turn your blinker off, just don't use your blinker. You went this way, but you went there. Old man angry. Alright. So what do you think the relationship is between logarithms and exponentials? An exponential takes a base, raises it to a power, and gets a number. A logarithm takes the number and tells you what the power would have been. Don't they do the opposite of each other?
And so they're inverse?
They're inverses of each other, yeah. So here's kind of a silly question. They're all silly, Jeff. Be quiet. What is log base 11 of 11 to the 7th power? This is a crazy, silly question.
Wait, what's that?
Yeah. So this problem tells you the answer. How many 11s do I need to multiply to be 11 to the 7th power? How many 11s do I need? 7 of them, right? Now, why does it make sense in the context of what I just said about inverses? If these two are inverses of each other, don't they cancel? What am I left with? 7. Yeah. So let me see if you guys get this one. What if I do, what do you got, Jeff? 15 to the log base 15 of m. Do I have an exponential function in here? Do I have a number being raised to a power?
Yes.
Yes. Do I have a logarithmic function in there? Are they operating kind of like on each other? What are they going to do?
Combine.
They're going to do what? Cancel. So what am I going to be left with? N.
That's weird. I still don't see all the inverses.
Let me ask you this. Remind me, the answer to this, what is it again?
3.
No, I mean, what does it represent? It is the answer to any logarithm is a power, right? Which is why the answer to this is 3, because that's what 2 needs to become 8. So let me say that again. Log base 2 of 8 represents the number that 2 needs as a power to make it become 8. Log base 15 of m represents the power that 15 needs to become m. Is that okay? Whatever the shit m is, I don't care. That represents the power that 15 needs to become m. Is that cool what I just said? And again, that's why the answer to this earlier one is freaking 3, because it's the power that 2 needs to become 8. So if this is the power that 15 needs to become n, if I raise 15 to it, of course I get m. If I raise 2, if this is the number that 2 needs to become 8, what do I get when I raise 2 to it? Freaking 8. So what's another way to look at that? These two functions cancel each other. These two functions cancel each other because they are inverses of each other. Just like cubing a cube root or cube rooting a cube.
I'll just type down the rule.
So, last thing for today. I want to graph this semi-nicely here. So at 0, what's the output? 1. At 1, the output is 2. And at -1, the output is 1/2. So let me write this down. So we got -1, 1/2, 0, 1, 1, 2. So everybody got that graph? Some of you guys are doing it in your head. That's neat. Can you take a moment and plot the inverse function? You all know how to do it. I've given you problems where I didn't even tell what the function was, and you still plotted the inverse
You
function.
literally just switch that so high.
Yeah. Give it away, why don't you? So if I want to do the inverse, what would the table look like?
1/2 of 1, 0, 1.
So let's see what happens. So at 1/2, it's -1. See this? 1/2, it's -1. At 1, it's 0. And at 2, it's 1. So far, it looks like it's going to be... Now, where was the asymptote, of course, for the original thing? It's here. Where do you think that goes when I do the inverse? Everything about my original function flips over the y equals x line, correct?
So it now becomes
So
the
it'll be on the
y-axis.
Now it's the y-axis. So this is going to look like And doesn't that do like we know it's supposed to have a mirror here, yes? So I know that. So this, let me see if you guys can do this. Can anyone tell me what function that is?
1 over x squared?
No. What's the base of this guy?
Oh,
2.
2. And we know this is a log because we already talked about logs or the inverses. So it's log base. What's the
2.
base? 2
2
of x. There we go. So I can get the graph of it. In fact, normally what I do is I do the graph first, but for some reason I decided not to do that. But I can get the graph of the damn thing without even knowing what the function was. We could have done the inverse function without even having a name for the inverse function yet. Just by changing the points and then connecting it. You guys semi with me? So exponentials look like this. Logarithmic functions look like this. Logarithmic functions are some of the slowest growing functions ever. That's going to grow forever, but it's going to get really flat really quickly. It's going to grow so freaking slowly, it's stupid. But eventually it's going to get to infinity someday. Right? So look at your calculator real quick. Can you do natural log? I'm sorry. Log. Let me say this before I forget. Don't worry about that yet. What's this symbol mean? So there really should be a 2 here, right? We don't write it because it's the most commonly used root. What's our number system based on? What number is our number system based on? 10 for some reason. I just don't know why. So when I have log base 10, I am never going to write that 10. The same way I'm never going to write that 2. We live in California. Hopefully it's not a big, like, whoa. What happens in California sometimes? The earth does crazy. Well, how is an earthquake measured? Richter scale. Richter scale is based on logarithms. Specifically, it's based on log base 10. So it's really funky if I have a Richter scale 4 earthquake versus a Richter scale 5 earthquake. It's not just a little bit bigger. It's hundreds of times bigger. It's 100 times bigger. It's 10 times bigger. Yeah. It's got a lot more energy than we think because it's based on powers of 10. Is there something else I want to say about that? No. So, real quick. In here, that I forgot. No, I forgot what I was going to do. Damn it. Let's see. If I do log of 1, I get 0. It's amazing. There's something else I was going to do and I just forgot. Damn it. I'll be fine. Oh well, too bad for me. If I do log of 10, yeah, it's going to be 1, because what power does 10 need? So whenever you see a log without a base, you know it's base 10. Just the same way you see a root symbol without a number, you know it's square root, second root. Same idea. Okay. All right. So I think that's enough for today. We'll have a little bit early for once. Don't forget about the quiz tomorrow, and then we'll finish up through 6-4. The updated homework sheet, the updated update is up on Canvas. Yes, the updated update. Okay. There's something I was going to do. Practice test and moving out tomorrow because the test is Tuesday. Practice quiz? What?
You don't have practice?
Never.